I'm recording. Oh yeah, no, it does for voice. The videos all have voice too. Yep. So yeah, it's 60x to the 4th divided by 4. So I want to reduce it down. So what is that? What's 60 divided 15? Yeah. So we have, don't forget, 15x to the 4th. All right, minus. So the next one is going to be 650x cubed over 3, correct? That does not reduce. Just leave it. Uh, 1200x is 1200x squared divided by 2, which is what? And then plus 4500x. What did I do? Oh, yeah, I forgot the squared. There you go. Squared. Thank you. And remember, we're going from, this is a definite integral. Definite meaning we have a lower and upper bound. We're going from where? 0 to 5. Before I do that, we'll cut through some of the math. I'm not going to make you sit here and do all this math, but just to give you a quick idea, I personally would go through and do what? I would get rid of the 5, because do you see everything is divisible by 5? So I would go through first and go minus 130 over 3. 650 divided by 5. Everybody with me? 650 divided by 5, 130. I can take this 650 and divide by 5. It becomes 130. I'm leaving the 3 there. Yeah. So 600 divided by 5? 120. And 900. Okay, so here's what's nice. Whenever you have 0, we learned this last week with evens and odds. When you plug in the 5 minus plugging in the 0, what happens when you plug in the 0? What does the whole thing go to when you plug in 0, everybody? It goes to 0. So like, oh, good. The only work you really need to do is plugging in the 5. All right, do you want me to just give you that answer? Do you want to sit and do all the work? You can. So it would eat, oh no, no. Again, problem with technology. You got it back. So yeah, it would be 3, 5 to the 4th minus 133, 5 cubed. Minus a big 0, because everything when you plug in the 0 goes to 0. That number is, you ready for it? 3,958 and a third. I don't want to waste the time going over basic calculations. So it's not the area. What is it? It's F bar. So let's talk about what that actually is. I'm going to go back up to the graph. So everybody got the answer. It's 3,958 and a third. Trust me on the math. Try it on your own. So when you come back up here, this was 6,000. So what it's saying is, oh, there's an average elevation. It's not the area. It's the average elevation. So when you took that height on that particular trail for the first 5 miles, you started at somewhere a little under 5,000 elevation. You then went up, and then you took a nice downhill. But if you could say, hey, my average elevation during the 5-mile walk was 3,900 and okay, it's not the area. The area would be before you divided everything by 5. Yeah. So the area would be much larger. But it's not an area, it's an average elevation. So if you think of it in terms of elevation, I think the average function makes sense a little more. That's why I do an elevation problem. This 0? Oh no, this is, remember when you do integration, you then have to plug 0 into all of these. But when I plug 0 into all of them, guess what I just get? 0. So I'm not going to do that. Okay, so that's an average function. The average function then leads us, I'm not going to do another example, it's a minor thing, I'll give you one on the test, just average function. What you're doing is taking your integral and dividing by b minus a, whatever b minus a is. In this case, it's 5. Okay, we already did it. We did it right here. We did it right there. We already did it as part of the problem. Why? Oh, divided by. Oh, right. No, it's 3,958 and a third. Yes. No, I was going to say, no, that number makes perfect sense in the context of our problem. I was wondering why you kept saying divide by 3. I'm like, there's nowhere on here we're dividing by 3. No, it's a third. Because there was a fraction. There was a fraction right there in our, that's all. I did the math, that's all. All right. So again, that'll lead us to the mean value. And again, don't want to spend a lot of time on this one either. Just kind of want to show it to you. I do want to spend a lot of time on substitution rule on 5.4. But the mean value theorem, and we'll go back and put it in the context of this problem as well. The mean value theorem for integrals simply states that you have some, of course, you've got some assumptions. F needs to be continuous, right? Because if F isn't continuous, it all goes out the window. We have a polynomial, so this always works great with polynomials. They're always continuous. So F has to be continuous on that interval of A, B. And the mean value theorem then says, hey, there exists a point C such that this C value, or F of C, is equal to F of bar, to F average. There, basically, it's saying there's some C value that's between A and B that is going to be exactly equal to that average. And I'll go back up to the picture in a second. There's some C value between A and B where F of C is the exact average of the function. So when you come back up here, I'll scroll back in a second, that's saying, hey, somewhere between 0 and 5, it appears to be right there. Do you see it? There's a C value where F of C actually equals 3,985 and a third. That's it. We're not going to find it for this problem because that polynomial is huge. And if I set that polynomial equal to the average, we need technology to find that X value, okay? A lot of technology. We're not going to do it on our own because it's like it's a cubed function. It just would take too long. But it exists. You can see it on the graph. It's there. That's all remember, that's all the mean value theorem ever says. Hey, there's something in the middle between A and B that is exactly equal to, in this case, the average function. That's it. Okay? That's all it says. All right? We're not really doing too much with that. But I wanted to finish off 5.3. And that is your mean value theorem for integrals. I'm going to get into what is probably one of the most important things you'll do as you continue with integration, moving past Calc 1. And that's 5.5, which is the substitution rule. Yep, exactly the same. No, get another book. Your math lab, depending on what you purchased. Remember when you all bought math lab at the beginning of the semester? Huh? Oh, yeah. There you go. You never used it? You didn't do any math lab problems? That's not good for your grade. Yeah. See, you've used it. The textbook's in there too. You might, those of you that are going on to Calc 2, how about this? I'll put together a list in case you get ambitious and bored with your family over the holidays. Say, hey, if you're going on to Calc 2, go back and review this stuff. How's that? Will that be good for you? I'll post it. I'll put a little list together because my youngest son's going from Calc 1 to Calc 2, and my older son, who's like done it all, keeps telling him, you need to do this, you need to do this. So I'm like, oh, I'll have him put a list together for you. So from a former student, I'll have him put a list together for you and say, this is what you really need to go back and make sure you know off the top of your head. Anyway, and he will say, U sub is one of the most important things. And that's what we're doing now. Okay? U sub is the reverse of the chain rule. So we're going to start with some chain rule problems to kind of get us used to it again. The reverse of the product or the quotient rule is something you will touch upon in the middle of Calc 2. You got to do like differentiation by parts, and it's all, you got to do integration by parts. It's a little more complicated. We're going to do the reverse of the chain rule. So let's take a look, okay? So let's go back to our chain rule real quick. So we're now on 5.5. All right, chain rule says, hey, so let's practice chain rule off the top of our head without doing the U's and the D's and all that stuff. Let's just practice chain rule. So we're going back to derivatives here. So if f of x is sine of 6x, all right, first of all, how did we do chain rule? We did, okay, there's an outer function, that's your sine function, right? You look at that 6x as your inner function, correct? So first, you take the derivative of the outer function, keeping that inner function as is. So what's the derivative of sine? Good. And you multiply it by the derivative of the inner function. What's the inner function? 6x. What's the derivative of 6x? So it's just this. I'm going to put it out front because I like it there better. See, you did chain rule without even going through all the steps. Let's do a few more. Let's suppose f of x, I had some examples, there it is, was 3x squared minus 5x, and that whole thing cubed. Okay, my outer function is anything cubed. Well, what's the derivative of anything cubed? Derivative now. And this is good because when you take that final, you got to go back and forth between derivative and integrals, right? You got to know which direction to go in. How do we take the derivative of something, anything cubed?
3 times function squared.
Yep. 3, and I like how you said that, times the inner function, we're going to call it, which is, you leave it exactly as it is, but you square it, times the derivative of that inner function, correct? What's the inner function? You can take the derivative of that function times, there, you just did chain rule. See how easy chain rule is getting? Good. We're going to do 2 more. What did you say? I just did. I started with trigonometry. I even started with it. Oh, come on. Let's do, no, don't dial me. My pen dies, I'm going to cry. I picked specific problems to lead into the lesson, Damien. I'm sticking with them. All right, ready? I'm in a good mood. You know why I'm in a good mood? I'm going to tell you why I'm in a good mood. I won my football pool this week, so I won $100. And I did not stay up. The real football. American. I'm sorry. I'm just joking. Sorry. I know. Sorry. I know you're a big soccer player. Anyway, I did not stay up and watch that game, though. But I happily woke up like, yes, I got $100. That's all I want. I wanted to win 1 week to win my money back. That's it. I got it. I did it. I'm good. All right, we're going to move on. Here's one. What did you say? I don't do well in Vegas. I do love craps. 5x minus 1. It's the only one that uses real odds. We're not going to talk about that in this class. I do discuss that in stats, though. Huh? I'd be a horrible poker player. I'd just start laughing. All right, let's do ln. Come on, what's ln? This is a good little review. The derivative of a natural log is just... Yes, because remember, the outer function is just ln, which is something over, right? That's all ln does. It takes it and puts in the... But then you need the derivative of the inner function, which is just... So it ends up being 5 over 5x minus 1. Okay? So here's what I want you to notice, because keep in mind, you're now going to be given the derivatives and you got to work your way backwards, right? So what you need to recognize is, hey, is there a main function and is there a derivative of that? So take a look. When you see cosine x, do you see the derivative of 6x? It's right there, right? Look at this next one, because remember, you're not going to be given the original function. In looking at f prime of x, can you recognize the derivative of the main function? So when you look at that, you see a 6x minus 5, you see this. Oh, wait a minute. Isn't that the derivative of that, right? As long as you have your derivative of your function in your integral, you can use u sub. And we can go backwards. If it's not there, sometimes we can put it in depending on what it is. But if the pieces you need aren't there and you can't put them in, you can't use u sub and you go, whoop, well, that's something I'll learn in like Calc 2 or Calc 3. Okay? All right? So it's recognizing. It's looking at an integral. These are going to be integrals and saying, oh, 6 is a derivative of 6x. 6x minus 5, oh, that's the derivative of 3x squared minus 5x. Right? 5 is the derivative of 5x minus 1. So now, instead of putting them in place, you need to recognize it. Okay? All right, I'm going to give you the theorem, the full theorem of u substitution, and then we're going to go ahead and practice some problems. So here's the theorem. Come on, pen. This is theorem 5.6. And it is the substitution rule of integrals. We're going to start, so we're going to evolve into the indefinite, no, we're going to start with the indefinite, sorry. We're going to start with the indefinite integral, meaning we're not going to have a lower and upper bound. We'll start with those, and then I'll show you how to do it with the lower and upper bound. That's the definite integral. All right, here we go. It is fondly known as u sub. That's what we call it. You say u sub to any calc student, they'll know exactly what you're talking about. Okay? So we're going to call it the u sub. And this is why. We're going to use u's to kind of help us out. So we're going to let Now, we're going to keep with the same idea as f of x, the outer function, and think of g of x as always that inner function, okay? That's why we're letting g of x just be u. So u is going to be the inner function. That's what I mean by that. Inner function. Okay. Of course, we have to have, yes, the function g is differentiable. You got to have these assumptions. You don't need to worry about them when you're doing the problem, but when you're stating a theorem, you got to have them in there. On an interval. Remember, it's indefinite, so we're not using a's and b's. And f is continuous on the corresponding range of g. So basically, whatever the range of g is, f has to be continuous on that range. And that depends on what g actually is. Again, we got to have those in for the theorem. You don't need to worry so much about it when you're calculating them. So here we have the integral. So see if this makes sense. We know we have a composite function. That's why we do chain rules and stuff like that, because we got these composite functions. So we got some composite function, meaning we have an outer and an inner function. In that integral, you should also see the derivative of the inner function. Okay. That is simply going to be equal to the integral of fu du. So what we're doing is taking our function, our complex function, creating a simplistic function using u, f of u, and we're just going to integrate that simple function. That's the idea. Okay? So let's take a look at example, and I'll write some steps down to help with the example. So let's start with the integral. Dx. All right, so the first thing you want to do is define your u. You got to figure out what your inner function is. So I'll do that in red. Step 1. You got to identify that u function. And you're going to write it out. And I'm going to tell you why you're going to write it out. You're going to need to write it out because you may need to come back and use it. So don't just say, oh, I can do it on my head, it's fine. That's going to cause you issues with some problems. So in other words, you would identify it, meaning, oh, u. So when you look at that, tell me what u is. What's your inner function? Yeah, does everybody see that? U is 2x plus 1. Okay? When you look at that, what's your inner function? Think back of all the derivatives, the chain rule.
2 is the derivative of 2x plus 1.
Right, so u is 2x plus 1.
But I thought u was the derivative of the.
We're just finding g of x. So when you come up here, remember, u is g of x. G of x is that inner function. Yeah, so do you see everything I got the squiggly line under it? That's our u's. Nope, that's your u. There's not going to be v's in this. Integration by parts has v's, and that's why you got to introduce other things, because that goes back to your product rule. This is chain rule, no v's. Okay? So recognize, remember, these f primes that we did first, are what you're going to see inside integrals. So you got to recognize what I have in these squiggly lines as your u, your g of x. Okay? Now, you defined your u. Go ahead, and I would, underneath of that, actually calculate du. The reason we're calculating du is because we got to make sure that's also in the integral. What's du? 2 dx. We're going to add the dx because you don't know what x is. Oh, sorry, that's calculate du. Calculate du. The reason you calculate du is it may not be in there. You might have to put it in there. So you got to calculate it so you know what it is. This is an easy problem. You know du is just 2 dx. Now you look at your original function. Watch. Yep. Because anytime you're taking the derivative, x is a variable that's unknown. So you expect dx.
Oh, you never did that when we were all this time. We never did that.
We sort of did. All right. Let me get back to that. Let me finish this problem. Okay. And I'll tell you, you'll see why in a second, why we do that. All right. So 2x plus 1 is your u. Is 2x plus 1 there? It's right there. Do you have the full 2 dx in that integral? Can you identify it? Do you have 2 dx? There's the 2. There's the dx. So now, just rewrite your integral using u's. If needed, and we will get to one where it's needed, but let me put it in here. Add in any constant to get du. All right, that second part you won't, until we do the next example, it won't make sense. All right, we don't need to add it in, it's there. The exact du is there. All right, so this now becomes the integral of 2 and dx becomes du of u cubed du. You just simplified it. Now you just turned it into something you can easily integrate. Can you integrate u cubed du? You can absolutely integrate u cubed du. So integrate with respect to u. All right, what's the integral of u cubed du? Integrate with respect to u. That means it's all u's now. So what does that come out to? U over. This is an indefinite integral. What do we stick in there, Kyle? Oh, it's in the original problem. Remember, you're replacing 2x plus 1 with u. So it becomes u cubed. Because that was the original problem. Yeah, so you rewrite this integral using u and du by substituting it in. So we let u be 2x plus 1, so we put 2x plus 1 there, became u cubed. Du is 2 times dx, that became just du. Once you get the hang of it, it'll be easier. It's not, it will, promise, get easier. The point is it becomes something we can now simply integrate. We integrated it, but we don't want our final answer to be with u. So your last step is simply let's write it this way. Let me do this. I will say replace u. Sorry. With the function. In other words, what does u equal? Yeah, so it becomes and that's your answer. What two? Where? It became part of the derivative. It gets absorbed. Look at what we did. You agree with this part? Okay. Right? Because du, 2 and dx gets taken out, and in 2dx's place gets put the du. Okay? The reason we can now integrate it is because the derivative was there in the problem. So all we have to do is integrate our u function. Becomes u to the fourth. Let me, here, do this. Go back to derivatives. That's why I started this way. Do you have a 6 sticking out? No. So keep in mind, what we really did, and I'll write on the board, what we really did is we now said, hey, this these things don't work. This equals that. That's what we're doing. The only way it works, though, is if that du is part of the original problem. It's not part of the answer. Because remember, we're going backwards, so you can think of this as the answer. It had to be part of the problem. If it's not, there are instances we can add it, and we'll go through a bunch of examples. I'm not going to write the steps for every example. We'll go through some examples. Has to be there. All right? Right. Well, look at this 6x minus 5. If you took the integral of this, is that anywhere in the original problem? Nope. It got absorbed. The reason it works is because it is there in the first place. That's why this works. The reason the u sub works, because that's there. Because that derivative is part of what you're integrating. All right? So you got the steps. I'm not going to write the steps out anymore. We're going to go through and do a bunch of problems. So.
What happens to the du? Is it like, why is it turned into a c?
Oh, it doesn't turn into a c.
Okay.
When you integrate, go back to what you can integrate. Right? Isn't that x cubed over 3? There's no dx in the answer, is there? No. That's no du. We put the c because when we did indefinite integration, we don't know where this is, right? It's a family, right? Because we're doing indefinite. We will do definite a little later in class after we practice some indefinites.
Well, what about the dx?
With dx.
The dx, why is there dx? You were talking before. Well, why is there dx in the integral?
So x is x is any variable. You don't know what x is. Okay, so ultimately we kind of always have a dx. We don't need it. We need it in this case because it's part of the integral. I don't know. I'm trying to figure out how best to explain that. Lucy, did you have a question or did you want to follow up with this? Let me see. Is it relate to the dx part? Okay, we'll go back to that.
But why is how come we did not use the dx in all this time and we're using it now?
So we kind of did. We always integrated. So, wrong marker, sorry. If you integrated back when we first learned derivatives, right? We said, okay, y equals 2x, right? So we would find dy dx and said, oh, that's just 2. We didn't add a dx. You wouldn't add a dx because what you would actually add, y becomes a derivative of y with respect to x.
Yeah.
So then that becomes dx with respect to x.
Okay.
Okay?
Okay.
Now we're doing, we want the derivative of u. So it's part of the integral. I'll come up with a better explanation, I promise, next week. I'm not coming up with it right now for you. All right? But because it's a variable, it's chain rule, essentially. It's always the derivative of whatever that variable is. Okay, we can leave it out. We're doing applications of derivatives. But when you're going backwards with the integration, you got to put it in there. If not, you'll be left with this lingering dx. Okay, so let's practice some to see if you can get the steps down, all right? Let's do another one. Let's do, I've got a bunch of them to try here. And you said you wanted to do the sine one, Lucy? You were trying to figure out how to go backwards from that one? So let's do it. So big. So you want to do integral. We know what the answer is, but let's use the steps of 6 cosine 6x. Okay? So when you look at this problem, first thing you want to say, okay, what's my u? U is that inner function. Think of cosine as the outer function. So what's the u, everybody? No, just the 6x. It's the inner function. Okay? F of x, if you, again, this goes back to composite functions that you learned in pre-calc. If f of x equals cosine x and g of x equals 6x, what's f of g of x, everybody? Cosine 6x. So what's your inner function? The 6x. The outer function is the cosine x. Goes back to composite functions. Okay? Now, real quick, right under that, put down what the derivative of u is with respect to x. So we're going to include that dx. U is what? 6 dx. Now, there's my 6x. Now I need 6 dx. Do you see 6 dx? There it is. Oh, du. I just forgot to put the d in front of the u. Sorry. I thought you were talking about this one. No, my bad. I just forgot to write the d in front of it. Derivative of x. We don't know what x is. It's dx.
Why don't you put dx over dx? Why isn't it dx like how we would do
Okay, now watch. Do you see the 6 dx? It's right there in the problem. If you do, it's not going to work. So we're taking the derivative of u times it. X is some variable. It's a chain rule times the derivative of whatever x happens to be. Because we don't know what x is. X could be anything.
So we're not taking the x that's on the inside of the inside function.
Yeah, and if x is just a single x, it is 1, but you're going to write it here. Because if you don't, you can't get rid of that dx in the problem. It's kind of always understood to be there, but if x is just a single x, yes. And if it is just an x, then yeah, dx is just 1, and we would not normally put it here. We're putting it in this place for the notation. We need the notation here. All right? So replace. Go back to your problem. The 6 dx becomes what? Du. And this becomes cosine of what? Yeah. Cosine u du. Now it's a simple integral you can integrate. What's the integral? What's the integration of cosine? Positive sign. Yep. I just want to make sure you know. Because remember, when you go in that direction, it's positive. It's sine u plus c. And what was u, everybody? Okay. So it's sine 6x, which is exactly what you get. Lucy. Well, this is the same as doing integral of cosine x dx, right? Is just sine x. You don't write, I'm not sure how it's removed. Once you do the integration, it's gone, yes. Once you actually integrate cosine u, the du is gone. Okay, let's do another one. Do e to the 10x. Do times 10 dx. Is it the inverse? It's tricky when you talk about it as an inverse. But yes, if you integrate the derivative, you'll get the function, right? Yeah. In which case, yeah. You just got to be careful when you're dealing with indefinites because of that unknown c value. But essentially. So, real quick. All right, looking at this, what's the inner function? You got to recognize that inner function. It's 10x. There's no negative there. No, I'm sorry. Oh, that's from on the board when I was erasing. Sorry. If what were a negative 10? You'd have to do them separately. And it would still be 10x. Okay? All right, so what's du? All right, I'll double line that. There's my 10 dx. Single line it. There's my u. So my new integral becomes e to the u du. You can integrate that. What's e to the u du integrated? Just e to the u. And last step, get rid of the u. And that's your answer. So what happens if it's not there? Integral 3x plus 5 to the 10th dx. Okay? I'm going to ask you again. What's the inner function? 3x plus 5 is your inner function. What's the derivative of that inner function? So you look for it. There's your u. Do you have a 3dx? No. If what you are missing is only a constant, you can introduce a constant. What is needed for us to, because if it's like it is, we can't do it. Can we put a 3 in place? Sure. Wouldn't I be able to do this if I'll stick it over here? That is a funky looking 3. Now do I have my du? But I just changed the value. What can I add to that to ensure I don't change the value of the integral? What can you multiply 3 by so it becomes 1? You can multiply by 1/3. Right? Any number can go where on an integral? Outside. Flip that on the outside. Now do I have my du? Now I can rewrite it. So if there's a constant missing, you can add any constant into that integral by putting 1 over that constant on the outside, because they cross each other out. That's just using algebra. Because without what's in red, we don't have the 3dx for this to work. We're missing the 3. Well, no, du has to equal 3 dx, because that's the integral of u, right? So I'm missing the 3. I mean, see, but if I say this, then you're going to get all confused with the algebra. You can think of it the other way is, okay, but that means dx is equal to du divided by 3, and you can replace dx with du divided by 3. It's the same idea. Believe it or not. It's the same idea. Either way, you're getting a division of 3. No matter which way you look at it, you're getting that division of 3. So you finish it. What's u to the 10th? Integral. Yeah, u to the 11 divided by 11. But don't forget, you're multiplying it by 1/3. And don't forget to replace it. What was it? 3x plus 5? Yep. Oh, yeah, I forgot to put the 11 back. I put it up there. I didn't put it in there. There it is. You can leave it like that. 11. That's an 11. do another one where it's missing. You can do any of them. Do the integral of sine. Well, let me show you this real quick. I want to show you something. Okay. All right. So u, what's u equal to? Correct? What's du then? X squared dx. Now, can I apply the u substitution rule here? I can introduce constants. What I cannot introduce are variables. The derivative in this case has a variable that is not in the problem. Do you see that? Does everybody see? 6x squared. The 6 is fine. I can put the 6 in there, but what can I put in there? There's no x squared. You cannot use this rule if you can't manipulate it in a way to get that derivative of u. Okay? You're not going to get that in a homework problem, but I want you to see that. Okay? This has to be done a completely different way that you are not anywhere near learning. Okay? It gets way more complicated. We're doing basic u sub, meaning we can do it if all I have to introduce is a constant. We cannot do u sub if what needs to be introduced has a variable component. You just go, nope, can't do u sub. You'd have to find another way to integrate it. Yeah. We're not doing that, no. All right. But now let's get creative. We are going to get a little creative with this next one, okay? Because again, algebra is a cool thing. You can manipulate a lot with algebra. Not enough to do that, though. You can't just introduce, I can't stick a 1 over x squared on the outside. No, that's not going to work because you can't pull an x squared out of the integration sign. The reason you can do the constant is you can pull that constant piece out of the integration sign and get it away from it. And it allowed you to introduce that 3, as long as you put the 1/3. Now this one's fun. You ready? Let's do integration of x over all right, so you get something like this, and when you reach a point where you've learned so many ways to integrate, you're just trying things, right? So if you were to try u sub, when you look at this, where's the inner function? Just what part? But what part of the bottom? Just what's inside the square root. You're going to the inner function. The inner function is x plus 1. Lucy? Okay. Everyone go with that? We got the inner function. You can take the derivative of that. What's a derivative? Dx. Well, that's great. I've got a 1 dx. But let's start to substitute and let's see what happens. If you start to substitute, I can put that in, correct? I can turn my dx into a du. But what's my problem? There's my problem. I only have u's in this. That's not going to work if you still have an x. I want you to look really closely, and this is why you have to write every piece down. If you think you're going to do it in your head, you're going to make a mistake. Can you see anything on what we've written so far for this problem that relates a u with an x? Lucy. Can, but would not still keep an x in the problem. Trying to get rid of the x, Kyle. Is that what you were going to say? It's right there. What does x equal, everybody? Because I can't integrate with two different variables. I need to have just one variable. Doesn't that mean x equals u minus 1? Well, let's try it. All right. I don't have a quotient rule for integration right now. This is where your algebra comes into play. At this point, you need to know your algebra, right? Can you figure out a way to take that fraction and to break it down? Lucy? You can? Which will come in handy at some point. So he goes, all right, u minus 1. But I still have a lot of integration. You have a common denominator. Can I break up my numerator into two fractions? Look at what I did there. Yeah, you're going to be able to look at fractions like this and break them up. Because when you break them up, now you have an individual variable and you can integrate. You can actually integrate now. You can integrate by saying, oh, well, that equals, I'll just do them, you can do them separately. It doesn't matter if you keep them together or do them separately. But let's do this. Look, I have a u to the first over u to the 1/2. Basic exponent rules. What do I do with my exponents, everybody? Subtract them. Isn't that u to the 1 minus 1/2? What's 1 minus 1/2? All right, so that part becomes u to the 1/2, right? Now, do the second piece. Oh, that's just u to the negative 1/2, isn't it? I can integrate those. I can absolutely integrate those. How? Tell me how. Technically, it never stops. And you may learn a method later on where you can integrate something like that. But more than likely, you're going to break it up. You're going to break it up. Yeah. It's kind of like if you had 6x squared minus 1 squared, you could FOIL it out. And the reason I use things like to the 10th power, you're not FOILing that out, right? You can though, but that is another way of doing it. It would just be really long. You can integrate this. Let's integrate it. All right. It's u to the 1/2. You increase it by 1, everybody, right? What's 1/2 plus 1? We can do this in our head. What's 1/2 plus 1? 3/2 divided by, I'll leave it like this. We will fix that. I don't like it like that, but we'll leave it there so you know where it's coming from. All right, what's negative 1/2 plus 1? You agree so far? That's just basic integration with fractions, though. You add 1 and divide by your new exponent. Okay? I'm going to clean this up. Yeah, I know there's a plus C. We'll put that in. And I'm going to clean this up. Division of 3/2 is multiplication of what? 2/3. So I'm going to make it 2/3 u to the 3/2 minus division of 1/2 is multiplication of I didn't say it was an easy problem. I said it was a fun problem. And your last step is just replace your u's. Just replace your u's. And you got to go. This is why it was important to write everything down. What did u equal? X plus 1. Can you write this clearer? Sure you can. For the test, you can leave your answer like that. There's all kinds of things you can do with that. I'll accept it like that. You don't have to go any further. Okay, you can factor out an x plus 1 to the 1/2, but that'll tax your algebra even more. So you can leave it like that. Kaya.
If you go back to the beginning approach,
Uh-huh.
why is the x plus 1 to the intersection?
So it's inside another function, a square root function. It's literally inside another function. Think of the square root function as the major function. It's inside that. That's why it's the inner function. If that x was under a square root, you're not doing it this way. You're not doing it this way. Things have to line up a certain way to use substitution. Okay? Fortunately, it does line up that way a lot. But things have to line up a certain way to use substitution. Okay? Same idea. But we're going to do it with definite. So what does that mean? We're going to put boundaries. We're just going to add the boundaries. All right? So let me put the definition down for you. Substitution rule for definite integrals. So again, we're going to let our u equal the inner function. Let me do this. Okay, u is always the inner function. We'll put our expectations in. Your g prime, which is your u prime, basically, your du part, must be continuous. So g prime. Because we are now putting boundaries in, it has to be continuous on that boundary. So basically, the derivative of your inner function has to be continuous. As long as these assumptions are going to hold for the problems you're going to do. On some interval. And then, of course, your outer function, your f function has to be continuous on the range of g. So it's whatever the outcomes of g is. I'm losing it. I'm definitely losing it. Looks like I have to switch. Maybe it'll come back. I might get it in. Let's try it. All right, here's what it looks like. Again, it's going to use f of x as the outer function, g of x as your inner function. So if you're originally going from a to b, of an outer function, g of x inner. You've got the prime there in the function. This is where it gets nice and easy. If you change your boundaries, notice the a and b. If you go ahead and change them to the outcome of g sub a and g sub b, you don't have to substitute anything back in for u. Let me finish. You don't have to substitute anything back in for u. You can simply take fu du, and you don't have to do the substitution back work. Yes? U equals g of x. G prime must be continuous on AB, and F, that's an F, my pen kept going out, must be continuous on the range of G. No, just F. Sorry, my pen was losing it. It's just an F. I like these because if you change your boundary, it saves you work. And here's what I mean by changing your boundary. We'll start with a nice, easy problem. Apparently there are no nice, easy problems. All right. Example A. Let's do the integral from 0 to 2 of 1 over x plus 3 cubed dx. Okay. So let's identify that g of x function. What does u equal? Remember, we use u. We don't, instead of writing g of x, u is your g of x function. Look at that. Now, we've done this a lot. Tell me what your inner function is. Just the inner function. X plus 3. Everyone agree? X plus 3? And we can do du is simply 1 dx, right? Okay. So you're going to take this one more step. Because we have boundaries, we're going to change the boundaries. Okay, you're going to plug those boundaries when x equals 0, okay? What's the boundary become? Yep. Our g of 0 is 3, or u equals 3. Our upper boundary is a 2. When x is 2, what's 2 plus 3? Change your boundary. Once you change your boundary, you never have to plug in the x plus 3 again. You can keep it as a u. It makes the problem that much easier. You can do it the other way, it's fine. You can find the full integral, plug it back in, and then do with the original boundaries. This just saves you steps by changing the boundaries, the lower and upper limits. So now my integral becomes, instead of a to b, instead of 0 to 2, what am I going from? 3 to 5. Instead of 0 to 2, I'm switching it to 3 to 5. Oh, I have u equals x plus 3, so it becomes what? 1 over... No. I just want to get this problem on here, and then I'll go to the board. I just want to finish this last problem. So what is it? 1 over... sorry. I got upset because my pen's dying on me. Shake it. If you shake it, doesn't that help the battery? Oh, it does. It does. And then my dx gets replaced with Okay? Say that again? That's a 3. Yeah, because a 3 is up there. It's a 3. You just have to finish that integral. You don't ever have to plug anything back in. You just do that integral. And we got our answer. And that's it. So, so let's rewrite it as the integral from 3 to 5 of u to the negative 3 du. Make sense? And finish it. Because we switched our boundaries, that's why I like the definite integrals better. You don't have to plug the x plus 3 back into the problem. So what is the integration? What is u to the negative 3, everybody? U to the, because you go up 1. Agree? This is a definite integral from, and just calculate that. You're done. So that is, I'm going to move it down. Negative 2 u squared, correct? Did I do that right, everybody? Look at my math. Huh? U to the negative 2, I move it down, it becomes positive 2. Okay. From 3 to 5. So it's negative 1 over 2 times 25 minus plus, because of the negative, 1 over 2 times 9. It's negative 1 over, did I do the 1 in the book? I can't remember. It's negative 1 over, it becomes 8 over 225. That's positive 8. You can do the fraction work on your own. Lucy. I had to subtract a negative. Because it ended up being negative 1 over 2 times 25 minus negative 1 over 2 times 9. There, I put it up there. I had to subtract a negative. That's why I made it positive. Kyle. I moved this down. It became negative. I just moved that negative out front. You don't have to. We could do it the other way. It just takes longer. By changing the... You have to end up plugging x plus 1 in. You got to square x plus 1. It just takes longer. You can do it. By changing the boundary, you don't have to plug in the x plus 3. Remember, we always had to plug the x plus 3 back in? You get the same exact answer. Like I said, you can do it without changing the boundary. You can keep it from 0 to 2. But if you do that, I'll show you. If you don't change the boundary, you go from 0 to 2. I'm going to use this piece. Actually, I'm not going to even do that part because we already integrated it. It's negative 1 over 2 times, what was it? What was the original problem? X plus 3. The original. Oh, plus 30. I mean, you can do that. You just now have to plug in 2 and 0 and do all the work. Where here, we just had to plug in 3 and 5 into a u. Now you're plugging into an x plus 3 squared. It's going to get to the same exact answer. You can think of it as a shortcut, but it's just showing you they're exactly the same. Pen seems to be going, so let's do another one. Let's do, what other one's good? That's hope. So here's the deal. The lab, normally, like I've been having them when we have a Tuesday test due Friday, so I can grade them over the weekend and get them back to you. I might still be able to do that. I'm away all weekend in Chicago. So if you turn it in to me by Friday, that's great. Maybe in my hotel room, I'll wake up Saturday morning and grade the labs. But I'll definitely grade them Monday morning. So Tuesday. Because we still have to review for a final exam. Your test is Tuesday. Huh? Yeah, it's the last day of the semester, Thursday then. For us, yes. Yeah. 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 We're reviewing for the final. The final is huge. On next Thursday, Damien! Next Thursday, we're reviewing for the final exam. It's our only day to review for the final exam. Gotcha. Those 2 days between Tuesday and Thursday is not going to make a difference for this test. You'll be fine. Let's do another one. Let's do... You can do the... Trying to pick one. I'll just pick one out of the book. Now, let's do a sine and cosine one. Let's do the integral from 0 to pi over 2. Let's do that. Mm-hmm. Mm-hmm. Any integral. Now, here's the hard part. Which of those is your inner function? Your inner function cannot be cosine x, because cosine x is not inside anything else. Do you see that? I want everyone to understand that first. Your inner function cannot be cosine x. Because that's just a function. It's not inside another function. What's your inner function? Sine x. Because what's happening to the entire sine x function? It's being taken to the 4th power. That's your inner function, the sine x part. The outer function is something to the 4th power. The inner function is what that something is. So your inner function is sine x, just sine x. So let's identify that. All right, and write it down. Again, you got to write it down. And what's a derivative of sine x, everybody? And you go, yay, I can use u sub. Why do I know right away I can use u sub? I've got the derivative sitting there. All right, let's change. Let's change, because we want to get everything in terms of u. So we're going to change our boundary in relation to that inner function. So you come over here. And I say, okay, my lower limit equals 0. Does everybody see that? My lower limit is 0, my original function. So what is sine of 0? Everybody knows sine of 0 is 0, right? Good. My upper limit, what's the upper limit? Pi over 2. What's sine of pi over? We use that inner function to change our boundary. Sine of pi over 2 is 1. So now my boundary goes from 0 to 1, which is good because we're going to work with u's. We're not going to work with sines and cosines anymore. This is why it's easier to change your boundary. Now we're just going to work with u's. All right, let's rewrite it now. U is sine x. What's happening to u, everybody? It's being raised to the 4th power. This is just du. So I just took a complicated trig, integral, and turned it into a simple u. That's it. This is all you need to work with now. You're done with that top one. That's all you need to do. So isn't that great? We just got rid of trigonometry in one step. What's a derivative of u to, integral? Sorry. What's the integration of u to the 4th? From just 0 to 1. Look how easy this problem just became. So it's 1 to the 5th over 5 minus 0 to the 5th over 5. Answer is 1/5. Done. Lucy. We took the lower limit of 0. And if you recall from the original theorem, let's go back to the original theorem for a second. G, which represents your inner function, which is your u, you replace the lower limit with what the value is at g. And you replace the upper limit with g sub b. So when we come down here, we took 0 and said, okay, what's sine of 0? Sine of 0 is 0. The upper limit is pi over 2. What's sine of pi over 2? Just 1. And we switched it from 0 pi over 2 to 0 to 1.
If you were to not like switch it,
Yeah, you can do it.
it would be like sine.
All right, if you don't switch it, again, if you don't switch it and you keep it 0 to pi over 2, right? Of u to the 4th du, we still get u to the 5th. If you don't switch it, you have to put sine x back. So it becomes sine to the 5th x over 5. Now, my question to you is, look at these two. Would you rather be calculating this, or would you rather be calculating that? Do you see the difference? You can do it. You'll still get 1/5 as an answer. It's not that bad. It's just an extra step. All right? It's quicker to change the boundaries than it is to plug the u back into the function. You're still going to get the same answer. In fact, this one's not even that bad because you have to go, okay, sine pi over 2 to the 5th over 5 minus sine. And watch. Basically, we did this. I can't see it. Up there. We did this up here in red. That's all. You just do it at a different point. We kind of did this calculation by changing the boundary. See, notice you still get the same answer. Because what's sine of pi over 2? You still get 1/5 minus 0. You still get the same answer. Okay? And this one wasn't too bad. Always easier, though, if you change the boundary. Okay, and that's what the theorem has you doing. And I think it's always easier to change the boundary. But if you forget to change the boundary, you got to put the x value back in, and you got to work it out a little more. That's all. Kyle? 5.5. 5.5. Yep, they're both in there, definite and indefinite. It does lead you to some very simple, I don't know how simple they are. I'll pull them up on the slide real quick. It leads you to some basic integrals, which if you're going on, this is one of the things I say, oh my gosh, just memorize these over break. Let me get into our class because I'll pull them up on a slide. So when you look at 5.5, these were the slides I had for it. Let me make it bigger. Okay. I should have it on the slide somewhere. And you can go through the notes, and hopefully the notes will make more sense to you. You can kind of go through. It leads you to these. You can choose to memorize all these if you want, okay? But doing substitution leads you to this idea. Because if we were to integrate cosine of ax, meaning your whatever ax is your inner function, cosine's your outer function, it always comes out to 1 over a times sine ax plus. So what some people do is they just memorize all these. Yeah, it's crazy. So there's different ones. But you don't have to memorize them because you can apply the chain rule. But they're general integration formulas. So if you were to look in the back of the calc book should have them. I know you guys don't carry around the book. Let me show you. Here's all your integration formulas. There's tables of integrals. You go to Calc 3, you'll hit on all of these. Huh? You have them online. Sure. Take a picture. Take a picture. Here. There's pages at the end of your textbook. So you can pull up your textbook online, and there's just tables of integration. Okay.
So you want us to memorize all of these?
No. Yeah. I want you to remember. No, I don't want you to remember. I want you to know how to do it. Okay. So yeah, if you use the table, and what happens is the ones you use the most often, what happens with those? You remember those, right? The ones you use the most often, you remember. But the idea is, hey, if I took the integral of cosine 6x dx, I've done this so often, I know it's 1 over 6 sine 6x plus c, and I'm done. And we kind of did one similar to this. We actually did one very similar to this. And why is it that? Well, what's your inner function? We're not going to do it, but let's pick out the pieces to it. What's the inner function, everybody, when you look at cosine 6x? 6x, right? What's a derivative of 6x? Is there a 6 in the problem? No, you got to introduce it. Hence, you get a 1/6 in your answer. So all these things we're doing, there are tables and tables if you progress. An engineer is not going to remember all of it. And there's tables and tables, 4 tables worth of integrals. Okay? So there's a lot. We are literally touching the surface in Calc 1 of your integrals. Just touching the surface. Yes. Calc 1, Calc 2, Calc 3. It will not carry you into differential equations, but it will carry you through Calc 1, Calc 2, and Calc 3. Nope. Discrete, yeah, linear is a totally different animal. I love linear algebra, but it's a totally different animal. You might come across something with integration in there, but it's a totally different animal. Differentials required. Some of them take linear. And here's the good news. If you're thinking of being an engineer, but this is driving you nuts, how much of it do you really think? I had lunch. We met the daughters. I'm going to have you get into your groups for a couple minutes, but we met the daughters' boyfriend's parents this weekend because they now live together in Baltimore. Thought it was time we met them. And he's an engineer, works at Picatinny Arsenal, which is a huge place to get a job around here if you're an engineer. And he laughed at me when I said I was a calc teacher. He goes, "Oh, all I ever remember is polynomials. I remember how to derive polynomials. I remember how to integrate polynomials. That transcendental stuff, forget it. And that's your natural log, your trig functions, your log functions. He never uses it. I'm not saying you're not. I'm saying don't panic, right? You'll use it in your engineering classes in college. You will do stuff. But anyway. All right. So the only thing I'm going to do Thursday, just so you know, I'm going to teach that little piece of 2 pieces. Actually, one of them's not extra credit, but I didn't have time today, and I think you guys are done today. I have 2 things. I got to go over applying. You'll like this. This is an easy one, I promise. Applying the integration to working backwards, meaning if you're given the acceleration function, you can work backwards now, right? You can get the velocity function from that. From the velocity function, you can now get the position function. So we're going to do an example of that. And then we're going to look at 6-2, integration of 2 curves. The first piece is not extra credit. That's something you should be able to work backwards. You should remember we've always touched upon that relationship between position, velocity, and acceleration. So we're going to touch upon that one more time. The integration between the area between 2 curves is going to be your extra credit problem. And then you're going to have a lot of time. We're just going to review, like I did before on there, go through what's going to be on the test. Left, I want you to meet with your groups right now. Those of you who were out, please get together with your groups. Those of you that, I'll put the group members up again. Those of you that were out, I have your test, because I know some people didn't come. Let me put your group members up if you weren't here and you don't know who your group is. But at least before you run off, meet with your group members before you go anywhere. Let me finish